You guys should have just finished your bell ringer, and if not, as always, feel free to pause me. It won't hurt my feelings a bit. In fact, I won't even know. But I tried to make it a little more doable. I got a little carried away last time, so sorry about that. Hopefully you'll be able to work this one. And it was beneficial for you. And again, we're just going to keep on doing those to keep getting you practice. Let me know if you don't know how to do those, and I'd love to, visit with you about how we can go through that maybe a little more carefully, and you didn't want to ask in class or whatever. It's fine. Feel free to, set up a time, give me a call, whatever. I'll be glad to make you a little video and send it to you. It's easy. It's no problem. So do try to ask for help throughout this second 9 weeks here, and that'll help us all succeed. All right, so the other day we talked about just a little bit about the periodic table, some of its history. You guys had what I thought was kind of interesting, cool homework. Cool is probably a little far, but interesting homework. And I think you guys are going to go over that after we do this lesson. And that'll kind of give you all the background you need for the periodic table. All right, so now we're going to kind of get into some of the more, I guess, sort of nuts and bolts of the periodic table, some of the trends that we see, and we always want to be able to use a tool to its maximum potential, right? So you don't just want to use a table saw just to, cut a board one way, right? You can cut grooves with it. You can cut very thin pieces. You can make the edge very straight so you can join up two pieces of wood together. And each of those is kind of a different skill and uses a different part of the tool that is, in it, but you can't bring it out unless you know how to do it. Okay, so there are some things in here in our periodic table, some trends in there that are really going to help us get into the structure of the atom at a very basic level. All right, so the first thing we're going to look at here, and we're just doing for 3, which is this page, and this page, and we'll talk through a couple of little examples, but that's it. But it's a lot of information, and so I want you guys to sort of put on your internalizing, absorbing hats, and not just your check the box and get the answer right, because you're going to have a real hard time with that if you don't internalize why these things are true that are true. All right, so check it out right here. 4.3.1 atomic radius. Of course, we know that defining the size of atoms is a bit tricky. Why is that? Well, he says right here, nucleus of atoms extremely small. Remember the, what is it, like a baseball inside of a whole football stadium is the comparison between the sizes, which is super tiny in the middle and super big for the electron clouds. Okay? And so the space that the atom takes up is defined by the electrons in their orbitals surrounding the nucleus. All right, and even those, remember, the size of the orbitals themselves is defined by the probability distribution. So remember, it's kind of this cloud that's like fuzzy on the edges and not a sharply defined deal. Okay, but they are able to zing these guys towards one another, and that strongly resists penetration by shells around other atoms, which is good, because guess what? If they all overlapped, we would not be able to feel things solidly. They'd always kind of be a little fuzzy, and but now we see and we know that those things that you're feeling when you clap your hands together like that, those are actually electron clouds resisting one another on the very edge of your fingers there, okay, which is super weird. All right, and just remember that most of that in here is actually empty space, okay, which again is super weird. Okay, so what do? Measure atomic radii by firing two atoms and how they bounce off, how closely they come before bouncing off. No idea how they do that. Do not know the process. Do not have time to look it up. I would love for one of y'all to look that up and tell everybody else about it. That would be super cool. If you had a video, you're welcome to send it to me. I'd love to watch it and share it. That really would be like actually cool. So somebody check that out. Nemo, I'm looking at you. Seems right up your alley. All right, let's look right here. Atomic radius values. 6 peaks of the alkali metals in periods 2 through 7. Okay, so what are those? Remember, our alkali metals are these guys here. All right, so they're the first in each group. I'm sorry, period. They're the first one in each period here. Okay, so lithium, sodium, potassium, rubidium, cesium, francium. They're the first ones. All right, so we've got hydrogen, helium, bam, next row, lithium, and then it falls, boom, sodium, falls, potassium, krypton is the noble gas all the way on this side, and then bam, rubidium, all the way down to xenon on that row, boom, cesium. Then things get a little wonky right here, okay, and you can probably guess and this has got to do with that D group of electrons. Okay, so that's cesium through radon. Cesium through radon. It's got a D. It's actually also got an F. And so you can imagine that maybe that does some weird stuff with the shape of an atom. Okay, so this is let's see, 1, 2, 3, 4, 5, 6. Those are your P orbitals. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So from here to here are your F orbitals. Okay, so you can see the wonky area is kind of all in that F orbital area, which is, remember, these guys down here. Okay, all right. Anyway, so convenient length that we're going to talk about is the angstrom. I know you guys are super excited about another unit that we can convert. Okay, but guess what? It's in our chapter and you're going to need to know it. So go ahead and write it down. All right, and do note that it has this guy. Okay, it's called a ring diacritic. You don't need to know that. I just wanted you to hear that. All right, and because it has that, because it's named after the Swedish scientist Anders Angstrom. All right, and I don't know if only Swedish people use that letter. I don't know a whole lot about that, but that's why it's a foreign language. So the angstrom, that is what it is. So like we say G for gram, kg for kilogram. It's capital A with the ring diacritic over it for an angstrom. Again, you will need to know that. Write that down. Okay? All right. So, angstroms. And look what they are. They're just 1/10 of a nanometer. Okay? 0.1 nanometers or 100 picometers. Okay? And that means that's 10 to the negative 10th. Okay? When if it's 0.1 nanometers, remember that nanometer is 10 to the negative 9th meters. It's 0.1 of those. So it's 10 to the negative 10th. That moves the decimal one more over. Okay? All right, what does that boil down to at the end of the day? Really, really small. Okay? And that should tell you how really, really small the nucleus is. If this angstrom, the radii are in the 1 to 2 angstrom, so that's edge of electrons to edge of electrons, and that nucleus is a teeny tiny little thing in the middle. This is the stadium. That's the nucleus. That baseball way down in the middle, so small you can barely even see it. And all that is just 1 angstrom, which is 1 times 10 to the negative 10th. So it takes 1 times 10 to the 10th atoms to make up a meter. Okay? That's a lot. All right. Just note through that. I'm sure you guys, again, have all read this and read through it. All right. So what is the pattern here? Okay. What's the pattern? We've got three things. We got first effect, second effect, third effect here. All right. First is the number of subshells, right? All right. So remember, subshells are subshell 1, 2, 3, 4, 5, 6, going down the periodic table there. Remember, these are subshells. Did I say subshells? I'm sorry. Those are your shells. These are your shells, and then your number of subshells. Hold on, that's confusing to me. I wonder if he meant to say shells there. Hold on, I'm going to pause y'all and let me read back through this for just a second. Okay, sorry, I got myself a little turned around there. He's using these subshells, basically saying the S subshell, which is the beginning of a new principal quantum number or a new shell here. He's using S as a new subshell as a stand-in for a new shell here. Okay, so again, he's drawing your attention to the fact that helium's way down here and lithium's way up here. All right, and then neon is way down here, and then you start on the new deal, and then we're on sodium. Even though it's only got one more electron, okay, it's got that whole new S shell in the, whereas neon's right here in the second shell. One more electron not only puts it down into a new subshell, it also creates a whole new shell. It moves from 2 down to 3. All right, so fluorine to neon is also only one electron, but that's fluorine right there, and that's neon right there. Okay, so see that very tiny difference with that additional electron. But when we add one more electron and go from neon to sodium, boom, it's all of a sudden a whole lot bigger. Okay? All right, so what does that mean? That means as we move down this, the atomic radii get bigger, okay? Which is pretty intuitive, right? More electrons, it gets bigger, all right? So that's the first one. The second effect is the increasing attraction between the nucleus and the electrons as we move from left to right across the periodic table in any given shell or any given period. Okay? So what does that mean? So if you'll look on your periodic table, flip back a page so you can be looking at this while I'm pointing at this. All right, so we've got potassium right here, K, and as we move across that period from left to right on the table, we end up at krypton, which has been steadily decreasing. Okay, now why is that? What did we say? We said it's the increasing attraction between the nucleus and the electrons. Well, why would there be increasing attraction? Because there are more protons. Okay, there are also more neutrons, but they're neutral. And so protons and electrons are positive and negative, respectively, and they are therefore attracted to one another. So you put a positively charged thing and a negative charged thing, and they're going to pull towards each other like a magnet. Okay? And they get more and more protons in the nucleus there, and so it pulls those electrons in tighter and tighter. Okay, so you can kind of think of it like I don't know, like a balloon has got the rubber on the outside, and as you can squish it down, and you can press all those air molecules down closer together until you get the same number of air molecules, but they're squished in closer. Okay, so that's what's going on. Those protons are in the middle, and they're pulling those electrons down. Okay, now we talked pretty extensively earlier that those electrons don't just collapse in there because of the Schrodinger equations and quantum things, and they've got waveforms, and their lowest energy is actually to be out there in the thing. But that doesn't mean they're not actually attracted and kind of crunched down a little bit. Okay? All right. So as we add more protons, as we add more protons, it pulls those electrons in closer and closer and closer. All right? So that means bigger, smaller. All right? Radii get bigger, radii get smaller. Okay? And then finally, the shield effect or atomic shielding. The electrons in shells with lower values of N effectively form an electrical screen around the nucleus and to some extent shield off the attraction of the positive nucleus for the electrons in higher shells. All right? Because of this, the electrons in higher energy shells are not attracted to the nucleus as strongly as we might expect. All right? So what does that mean? Well, he's using that shield effect to say that these electrons in the, what is that? So this is lithium to neon here. So we've got a 2s, 2p. The 2s and the 2p, when you come in here and you add this sodium, that final electron, these electrons sort of form a cover around it to where these electrons out here don't feel quite the same pull. So if we just had this electron and these guys weren't here, okay, but of course we know from the Aufbau principle that we couldn't ever actually have that, right? Because we always build up through these shells. But let's just say we were able to control that, okay? And we pulled these away. All of a sudden, this electron would be, he'd be pulled in a little bit closer because these guys wouldn't be shielding him anymore, okay? So that doesn't actually give you a direction on the periodic table, like gets bigger this way or gets bigger that way, okay? But it does tell you why this is so big right here, okay? So this is part of the explanation of this is the electron shielding. So we've added a shell, but why? It's not just a bump like that, okay? It's a bump all the way up here. The shielding explains why it doesn't stop here and why it goes all the way up to here, okay? All right. So basically, the long and the short of it is that you need to know they get bigger this way and they get smaller this way. It might be easier for you to remember bigger this way, bigger that way. Okay? So it may even just be easier to remember what's the biggest element we have. Francium. What's the smallest element we have? Well, hydrogen's not helpful because he's really in the wrong, because he can act sometimes like he's over here. But helium, we could say, is the next to smallest, and francium is the biggest. Okay? Biggest, smallest. Biggest, smallest. Okay? If you can just remember that, you don't need to remember a whole bunch about the directions and this and that. You just remember francium's the biggest. Boom. All right? And then you can you can work back into the rules that way. Okay? Because I don't know, see on a quiz maybe as we move down the periods of the periodic table, do atomic radii get bigger or smaller? Or as we move along a period from right to left, do atomic radii get bigger or smaller? Just throwing that out there. That could end up on maybe a quiz or maybe on a quiz and a test. I don't know. I'm going to ask the guy who's writing those quizzes whether they'll be on there. All right. So we've got 1, 2, 3. That's the main takeaway from over here. All right. And then the other thing is a little bit of an add-on to that, but it's a pretty intuitive add-on to it. Okay. So an ionic radius right here. Okay. What are we talking about with ions? What does that mean? Okay. Those are charged particles. All right, because we remember that in its neutral state, these guys have, if they've got 23 protons, they've also got 23 electrons, and so they're plus 23, minus 23, coming out to a 0 charge. Well, in the wild world of chemistry, that sometimes doesn't just stay that way. Okay, so you can gain or lose electrons. Okay, I think we mentioned that earlier in the year that, chemistry is all about electrons. Only a very small part of nuclear chemistry is actually dealing with any change in protons or neutrons. Okay? So it's all about electrons. All right, so does this define... Did we talk about anions and cations last time? Yes, we did. All right, good. Sorry, I thought it was in this section, but I already talked about it. All right, so remember we had cations, losing electrons to become cations, and gaining electrons makes you an anion. Okay? All right, so metals ionize by losing electrons to form cations, positive ions. The loss of an electron leaves an atom with one more proton than an electron, and thus the atom possesses a net positive charge. Makes sense. You lose a negative charge, you end up with an overall positive charge. All right? And what he's pointing out right here, group 1 and group 2. Let's flip back right here. So we've got group 1, group 2. All right? These guys always form a +1. They always want to lose one electron, okay? And that gives them a +1 charge. These guys always want to form a +2. They want to lose 2 electrons, okay? These guys don't do anything, okay? They're the noble gases. All right? They've actually got a 0 what's called an oxidation state or a ionization charge. Okay, they're a 0. They don't like to do anything with anybody. All right. These guys always want to form a -1. They want to gain an electron from wherever they can. These guys always want to be a -2. Okay, and then outside of that, things get crazy. Okay, so we can't make any predictions about anything other than +1. +2, -2, -1, 0. Okay? Go ahead and internalize that because we're going to be coming back to that again and again and again in the coming chapters. Okay? All right, and I'll just go ahead and give you the rationale, and then I'll give you the rationale about it next time too. You saw in your Asimov thing the law of octaves. So we have 1, 2, 3, 4, 5, 6, 7, 8. Okay? And we got all this transition stuff in the middle. 1, 2, 3, 4, 5, 6, 7, 8. Okay? Everybody wants to be like the noble gases. They want to have 8 valence electrons. And we will talk about what that means. Just roll with me. Right? They want to have 8. Well, what's fluorine have? 1, 2, 3, 4, 5, 6, 7. So to get to 8, he can go 1 in this direction, gain an electron to have a -1 oxidation state. Or he can go 1, 2, 3, 4, 5, 6, 7. He can lose 7 and become like helium, or gain 1 and become like neon. What do you think is the energy advantageous action for him to take? Gain 1. Boom, right here. Okay? Lithium could gain 1, 2, 3, 4, 5, 6, 7 and become like neon, or he could lose 1 and have an electron pattern like helium. Guess what he's going to do? He's going to lose 1 to become here. All right, so everybody wants to take the shortest route, the least energy-intensive route to become like these guys. All right, so there's not a whole lot of memorization that needs to happen here. Okay, these need to gain an electron to go here. These need to gain 2 electrons to go here. These guys need to lose 2 to be like here. These guys need to lose 1 to be like here. Okay, everybody wants to be like the noble gases. All right. All right, but right now, all we're talking about is what happens when what about that ionic radius? Okay, so what happens? Atomic radii blue and the ionic radii yellow. So blue is the normal neutral, and then yellow is the radius of the atom after it has ionized in the way that it likes to ionize. So remember we said lithium, sodium, potassium, rubidium. Lithium, sodium, potassium, rubidium like to ionize. Boop. Plus they want to lose 1. Well, guess what? It makes sense that their ionic radius, the yellow, is smaller because they've lost an electron. Okay, they haven't lost a shell, so it's not a huge amount difference. All right, but actually here they actually have lost a shell. So what is he? Let's actually look at that. That's a good point. All right, so let's look at this. We got the neutral one is 1.3, which we see right here. Looks like it's actually a little bit above 1.3, but maybe he's rounding it. No, he puts a 0 on there, doesn't he? That's interesting. It's not right on the 1.3 line over here. So anyway, we'll go with it. We'll say 1.3, and then what does it become when it ionizes? 0.9. That's a pretty drastic change right there. That's interesting. Okay, so a big change between those two right there. Let's see, what is that? 0.4 difference. This is 0.44 difference. This is 0.48 difference. Okay, so that looks like it has about a 0.4 angstrom difference here. That's interesting. I never really looked at these numbers before. So anyway, but you see on these guys, the ionic is smaller than the regular because it's losing one, right? And look at it's over here, as we would expect, it's the opposite. Okay? They're gaining one, so their ions are actually bigger. Okay, so because these guys are losing ions to become positively charged. These guys are gaining ions to become negatively charged because they're trying to get to that stable noble gas configuration. And that leads these guys' ions to be bigger, and these guys' ions are smaller. Okay, so you see how we could get into like a whole lot of memorization rules, a whole lot of stuff that's like, I just need to memorize that group 1 and group 2, they get smaller when they ionize, and group 16 and 17, they get bigger when they ionize. Or better, we could just say, okay, what happens in group 1 and group 2 when they ionize? They want to have a +1 and +2 because they want to move to get to that noble gas. That means they're losing electrons. Does that make things bigger or smaller when they get lost? Well, they lose stuff, they get smaller, boom. Nobody's asking about these numbers. Nobody cares about these numbers, but look these up. But what you are going to need to know is that 1 and 2 get smaller when they ionize, 16 and 17 get bigger when they ionize. Okay? And you need to know, when I ask you, and justify your answer, you need to say, because group 1 and 2, when they ionize, lose electrons, and when you lose electrons, your radii get smaller. And when 16 and 17 ionize, they gain electrons, which means that they are getting bigger because they have more electrons. Okay? You see how that's a justification for that answer and not just 1 and 2 get smaller because they're losing and 16 and 17 get bigger. And you just rotely memorize that. That was my robot voice, by the way. But then I snapped out of it there for a minute. Okay, so that's the main point there. Let's see what else we have here. Since the metal's always ionized, we're losing the electrons. Okay, so let's look right here at example 4.1. Okay, and I'm going to write these down real fast so we can not flip back. All right, so S, Se 2 minus 0, 0. O for oxygen, and S 2 minus. All right, so we got sulfur, selenium, oxygen, and sulfur 2 minus. Okay, and so what often is written here, this is how you write the oxidation state. Why they put the plus or minus after, I don't know, especially since the nomenclature is that this is a +1 here, and you don't write it like this. It blows my mind. But anyway, when you're writing an ion, this is how you write it. Okay, I'm going to ding you points if you don't write it correctly. Okay, so it's a lot like your 1s2, 2s2, 2p. Okay, except now it's got a plus or minus on it. Okay, all right. So let's look over here. What are we doing? All right, we want to go in order of decreasing size. So we want to write big to small, 1 to 4. Okay, so what do we have? How are we going to make this decision? Okay, well, they've given us sulfur, oxygen, and selenium. Okay, so we're not even going to talk about the rule. We're just going to remember that francium is the biggest. Okay, so big down and big this way. Okay, so going down, oxygen, and then sulfur, and then selenium should be the order. Okay, so we've got oxygen, sulfur, sulfur, and selenium. Okay, we've only got one selenium, and we got 2 sulfurs and only 1 oxygen. So this is your predominant, change right here. So we're going to go ahead and add this in right here, and that's my oxygen right there. Right? So the only question now remaining is this the ion or is this the ion? Okay, so we've got. I have written these backwards. I'm so sorry. We're going from big to small. Is that what it says? Decreasing? Yes. All right. So big to small. So big is this way and this way. All right. So we're going to write them. All right. Biggest is on the bottom here. All right. So for sulfur, is it going to be bigger if it has a 2 minus or bigger if it's just a neutral? Well, a 2 minus indicates that these are plus 2 electrons. So we're adding to this guy. So he's going to be bigger than his neutral brother over here. All right, so biggest is down on the bottom. And then this is sulfur with 2 extra electrons. Then sulfur with just a neutral electrons, and then oxygen with a neutral number of electrons. Okay. All right. So that's something we'll have to Se2, S2, S, and 0. All right. All right, and then one other one. Well. Y'all just work through that one if you've got time. I was trying to stop at 30 minutes here. So, okay. Well, y'all talk through your Asimov homework. If you have any questions, Miss Barron is going to have the, sort of the proper answer there. And let's see, what else? What's coming up? Let's talk for just a second about what's coming up. Okay. All right, so we're going to hit 4-4. And then on the 18th, so a week from today, you guys are going to have a quiz. And I really, really want y'all to be ready for that. Okay, that's going to be super good for you to be ready for that. So let's just make sure you stay on top of that, get the general ideas of 4-1 to 4-3. And that should be it. All right, so y'all go over Asimov questions, and that should take you guys about to the end of your time. All right, I'll talk to you guys soon. Look, I have a Flowwood board meeting on Monday where we would have a session. So I think we're going to have a session on the 22nd. And I think it's time for us to do it up at the school. So we'll try to do that. But kind of be eyeing that date, the 22nd, for a Monday, a Monday session, because we won't be too far from our test, which is on the 30th. Okay. All right. So let's stay out on top of that. Stay out in front of that. And we are also going to be doing an experiment in there too, and we'll be coordinating that, and I'll get you guys geared up for that as well. All right. Sounds good. I will talk to y'all soon. Let me know if you guys have any questions, okay? Thanks. Bye.